All right, welcome to day 6. We're going to do derivatives of polar functions and also do tangent line equations for polar functions. Our first homework one, we were doing an arc length. So your dx over dt is just your arc sine rule, 1 over square root of 1 minus t squared. For dy over dt, it's derivative of the inside over the inside. So for derivative of the inside, you had to do a chain rule. Then over our inside, if we neaten that up, that minus 1/2 goes down to the bottom and just makes it a 1 minus t squared. And then negative 2t times a half just gives us negative t. So our arc length integral, we have square root of each of those squared and then added. When we square those, we can then get a common denominator by multiplying the first fraction by 1 minus t squared. When you multiply that first fraction by 1 minus t squared, and then combine like terms in your numerator, the 1 minus t squared and the plus t squared will just give us 1. Well, we can take the square root of each of those. We get 1 over 1 minus t squared. Well, now that factors into 1 minus t and 1 plus t. So we can do partial fractions, pick some strategic values of t, 1 and negative 1 to find what a and b are, and you get a half for each of them. And then do your antiderivative. In the first one, we have a correction of negative 1 with our natural log because we had a minus as our coefficient. And the second one, we didn't have to correct. Sub in your 1/2 and your 0. Well, we have a minus 1/2 natural log of a half. We have a plus 1/2 natural log of 3/2. And then the other ones are just zeros. So really, we're going to have 3/2 over 1/2 inside the log, which is just 3. So 1/2 natural log of 3. So not an easy algebraic one to do, but it can be done with things that we have learned. For number 1, we have 4 comma 3 pi over 6. Well, 3 pi over 6 is pi over 2, so we're just on the y-axis and with a radius of 4, or 4 from the pole, I should say, so we just have 0, 4 as our point. For number 6, we have negative 3 and minus 1.57. Well, 1.57 is essentially pi over 2. So if we go backwards 90 and 3 away from the pole, but in the opposite ray, that actually puts us at 0, comma 3. In 11, our point was 1, 1. So if we do 1 squared plus 1 squared equals r squared, we get 2 equals r squared, so r is equal to plus and minus radical 2. If we do tan inverse of 1 over 1, we get pi over 4 for a reference angle, and tan is positive, so it's in either the fourth or the third quadrants. Note that 1, 1 is in the first quadrant, so however we write our point, it needs to be end up in the first quadrant. So if you use pi over 4 as your angle, we would want the positive radius, so we stay in the first quadrant. If you use 5 pi over 4, which would be a 45 reference angle in the third quadrant, we would want the negative version of our radius to send us back to the first quadrant. And technically, you could have either of those angles plus or minus 2 pi, and that would still be correct. For 13, we had negative 3, 4, so do negative 3 squared plus 4 squared equals r squared. You end up getting that your radius is plus and minus 5. When you do your tan inverse of your y over your x, that'll give us a decimal value. So we get either negative 0.927 for our fourth quadrant option when we are having a negative tan, or if you add pi to that, you get 2.214 for the second quadrant option. Well, negative 4 comma 3 is in the second quadrant, so when we do the 2.214, we would want the positive option of the radius 5, and for the other one, that is in quadrant 4, so we'd want to send it to quadrant 2, so we would have the negative option for the radius. So we want to convert the rectangular equations to polar form. So x squared plus y squared is just r squared. X is r cos theta. So you can add the 2ar cos theta over and divide by r, and we've got r by itself equals 2a cos theta. In 23, we start with y equals 4. Well, y is equal to r sine theta. Divide the sine theta over, so you can do either 4 sine theta or 4 cosecant theta. X equals 10. X is equal to r cos theta. Divide the cos theta over, so either 10 over cos theta or 10 secant theta. Again, x is equal to r cos theta, y is equal to r sine theta, so subtract the 2 over, pull out the r, and divide over. And you get r is negative 2 over 3 cos theta minus sine theta. In 26, sub in for your x and your y. We'll divide the cos theta and the sine theta over. Take the square root, so we'll have plus or minus that. And you could also write it as 4 secant theta cosecant theta under the radical if you want it. Again, fill in your r sine theta for y, your r cos theta for x. Divide your sine squared theta over, and also divide one of the r's out, and you just get r equals 9 cos theta over sine squared, or you could write it with your reciprocal properties as seen there as well. Starting with 29, we want to convert to polar equations. So r is the same as square root of x squared plus y squared. And when you square both sides, you just get a circle equation with a radius of 3. So originally I would say think of, because x is equal to r cos theta, think of your cos theta as equal to x over r. So then we have r is equal to 5 times x over r. Multiply your r over and you get r squared equals 5x. And then your r squared is just equal to x squared plus y squared. That might be a little easier to think about than putting the square root of x squared plus y squared in right away. Well, there you have your r is your square root of x squared plus y squared. Theta is your tan inverse, or you could say arctan of y over x. And if you wanted to bring it as regular tan over the other side, you could do that as well. It was kind of a cool looking graph for that one. If theta is equal to pi over 6, tan inverse of y over x is 5 over 6. So tan of 5 over 6, that's going to be a 30-degree reference angle in the second quadrant. That would be 1 over negative radical 3, or in other words, negative radical 3 over 3, and that's equal to y over x. And you can multiply the x over, and then it's just a line with a negative slope. 3 secant theta is the same as 3 over cos theta. Multiply the cos theta over with the r. R cos theta is just x, so you get x equals 3. And for these, you were just graphing and then do your menu trace. And you wanted to go through to see what interval was one trip around. So you had 0 to 2 pi for the first two, and then 0 to 4 pi for 43. So today we're going to look at slopes of polar functions. So first off, our polar functions are always r equals and something in terms of theta. Our variable on the right side has a theta in it. Well, first let's talk about what the slope equation is not. It is not just dr over d theta. And let's show you an example of why that doesn't seem to make sense. So if it was dr over d theta, then if we have r equals 2 cos theta, that would just be negative 2 sine theta. Well, at the point negative 2 comma pi, which would be this point right here, because pi would be going to the left on the x-axis, but then the negative 2 radius sends it through to the other side. Putting pi in for our theta and our slope would say negative 2 times 0, so that would say our slope should be 0. But it's pretty clear from that vertical tangent line that it should be undefined for our slope. So that seems to contradict right there. One more example, say you had radical 2 comma pi over 4. So pi over 4 angle is right here, and there's radical 2 out. So we're working with that point on our circle. If you put pi over 4 into your sine theta, that would be 2 times square root of 2 over 2. Sorry, I forgot the minus on there. Minus 2 times square root of 2 over 2. So that would give us minus radical 2. Well, that slope is clearly horizontal. It's not a negative slope, so that contradicts it as well. So this is just a couple concrete examples to show you why it is not dr over d theta. So you're probably asking yourself, what function is it for the slope? Well, let's go back to the idea that x is equal to r cos theta. Therefore, x can be thought of as a function of theta times cos theta. Because r can be represented in terms of theta. And we had y equals r sine theta. So again, whatever r is represented as times sine theta. So just an example, if we go back to the previous one, here's an example of an f of theta. So maybe r is being replaced with 2 cos theta or something like that, but some function involving theta. So our derivative, dy over dx, imagine we multiplied them both by 1 over d theta. Well, now it comes dy over d theta over dx over d theta. So let's do our derivative of our y with respect to theta. We would get f prime of theta times the regular sine theta plus, because we got to do a product rule, regular f of theta times derivative of sine, which is cos of theta. So that's the derivative of our y part. So now dx over d theta, we'll just use our f of theta cos theta. So we'll have derivative of our radius, derivative f of theta, times regular cos theta, plus regular radius, the f of theta, times the derivative of cos theta, which is negative sine theta. Now this is all assuming that the dx over d theta is not 0, because that would make it undefined. And we have that written out down on the bottom. So if you want to find your slope of a polar function, it's really a product rule we're doing. And we're doing the product rule of our radius times sine theta in the numerator, its derivative, and the radius times cos theta, its derivative in the denominator. If we want to have a horizontal tangent line, we would want our slope to be 0. So therefore, that would mean our top, the dy over d theta, would need to be 0. If we want a vertical tangent line, that would mean we want a slope to be undefined, so we would want the denominator to be 0. So we would need dx over d theta to be 0. So our first example we're going to look on the next page in the notes is we're going to find our slope at certain values of theta. Well, if we want to find the slope, that means we want to find the derivative at those certain values of theta. So let's list out what y and x are represented as. Y is equal to r sine theta, and we were originally going to talk about the polar function 2 cos theta. So y is really going to be 2 cos theta times sine theta. And x is going to be 2 cos theta times cos theta. Or in other words, we could write that as 2 cos squared theta. Well, now let's do our derivative of the y part and derivative of the x part. So derivative of the y part, do derivative of your first thing. Derivative of 2 cos theta will be 2 sine theta times the regular sine theta. Then plus the regular radius, so regular 2 cos theta, times the derivative of sine, which is just cos theta. In the denominator, we've got 2 cos squared theta when we neaten it up, so we'll just do a chain rule for that. So we'll have 4, keeping cos theta the same, times the derivative of the cos theta, which is negative sine theta. So neatening this up a little, we can say 2 sine squared theta plus 2 cos squared theta over a minus 4 cos theta sine theta. And we are going to use that to find our slope at each of those values of theta, at pi, pi over 4, and 2 pi over 3. So let's start it out at pi. So dy over dx is going to equal 2 times whatever sine of pi is squared. Well, sine of pi is just 0, plus 2 times whatever cos of pi is squared. Well, at pi, cos is -1, so we'll have -1 squared. Then on the bottom, we're going to have -4 times whatever cos is, which we saw was -1, times whatever sine is, which we saw was 0. Well, this is going to give us 2 over 0, so our slope at pi, we would say, is undefined. And if we look back to our picture, remember this was the point pi comma, or -2 comma pi. That was a vertical tangent line, so that being undefined makes sense. All right, well, let's try it at pi over 4 now. So we've got dy over dx is equal to 2 times whatever sine is squared. Well, at pi over 4, we're working with a 45, 45, 90 triangle. So because it's getting squared, I'm just going to leave it as 1 over square root of 2. Then we'll have 2 plus our cosine being squared. So we got to go back for 1 second. I made one tiny error up here in the dy over d theta. Derivative of 2 cos, derivative of cos is negative sign. So that should be a -2 on that there. So we had -2. That's -2, but it's not going to change anything. And that's -2 now. Sorry about that. So we would have for cos, we would have 1 over square root of 2 again, squared. On bottom, we have -4 cos theta sine theta. So that's -4, 1 over radical 2 for cos, 1 over radical 2 for sine. So 1 over square root of 2 is going to give us 1 over 2, times the -2 will give us -1. This will give us +1. On the bottom, 1 over square root of 2 times 1 over square root of 2 is 1/2, times the -4, which will give us -2. So this is going to give us 0. And remember that was the other point that we looked at. We looked at square root of 2 comma pi over 4, and that was a horizontal tangent line. So it looks like our formula is making sense. So one last one we're going to look at. Oops, I didn't change it over there. So I'm going to carry that down so we don't have to keep looking up. So we have the -2 sine squared theta plus 2 cos squared theta over -4 cos theta sine theta. So at 2 pi over 3, we're working with a 60-degree reference angle in the second quadrant. So we'd have -1 square root of 3 and 2. So we're going to have dy over dx is equal to -2 And we'll have our sine part squared. So square root of 3 over 2 squared. Plus 2 times our cos part squared, which would be negative 1/2 squared. Then that's going to be over negative 4 times our cos 1, which was negative 1/2, times our sine 1, which was square root of 3 over 2. So if we neaten this up, square root of 3 over 2 squared will be 3/4 times the negative 2 will be negative 3/2. Negative 1/2 squared is 1/4 times 2, which will be 1/2. Negative 1/2 times negative 4 is 2. 2 times square root of 3 over 2 is square root of 3. Negative 3/2 plus 1/2 will give us negative 1 over square root of 3. So you could leave it as that, or you could write it as negative square root of 3 over 3. So that's how you would find your slope at given points. What we're going to do on the bottom is we're going to work with finding tangent line equations. Well, part of what you have to do with a tangent line equation is you've got to find the slope. So that's the graph of 4 cos 3 theta there, and we've got 3 tangent lines at our pole. The pole is at 0, 0. Well, what we can do is we want to figure out what values of theta will be when we have those tangent lines. So we're going to work with r equals 4 cos 3 theta. That's the equation shown. So we're going to set that equal to 0. And this will allow us to find the values of theta where we will have tangents at the pole. So I should say tangent lines that pass through the pole. So if we divide the 4 over, we got 0 equals cos of 3 theta. And we got to think about when cos is 0. Cos is 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So we're going to start out, we'll set pi over 2 equal to 3 pi, or 3 theta, divide the 3 over, and we'll get theta is pi over 6. So that's one value of theta we're going to work with. Next, we're going to do 3 pi over 2 is equal to 3 theta. We'll divide the 3 over, and we get pi over 2 is equal to theta. So that's another one that we're going to work with. And the last one that we'll work with, and I should have mentioned, we could trace this graph, and we would find that it does a complete cycle in pi. Or the other way you could know that is we would have to do this 3 times because they're showing us 3 tangent lines. So the next one we would want to do is 5 pi over 2 is equal to 3 theta. So that's going to be theta equals 5 pi over 6. So we want to find the tangent line equations for each of those. Well, notice the point we're going to work with when we do our tangent line is 0, 0 for all of them. So we've just got to find the slope, and then we'll do y minus 0 equals the slope times x minus 0 in each case. Well, keep in mind that our y, which is r sine theta, is going to be 4 cos 3 theta sine theta. Our x, which is r cos theta, is 4 cos 3 theta cos theta. So when we do our derivative, dy over dx, we'll do the derivative of the y part first. We're going to have 4 cos 3 theta's derivative, which would be negative 4 sine 3 theta times 3. And that's coming from chain rule, times the regular sine theta, plus regular 4 cos 3 theta, and then derivative of sine theta is cos theta. In the denominator, the derivative of x with respect to theta, the derivative of 4 cos 3 theta, again, is negative 4 sine 3 theta. times the regular cos theta plus regular 4 cos 3 theta times the derivative of cos theta, which is negative sine theta. So let's call this case 1, this case 2, and this case 3. So for case 1, dy over dx is going to equal negative 4 times something times 3 times something. We're putting in pi over 6. 3 times pi over 6 gives us pi over 2. Sine of pi over 2 is 1. Sine of pi over 6 is 30 degrees. So we're putting in a half. Then we've got 4 plus 4 something times something. Well, when we put pi over 6 into 3 theta, we get cos of pi over 2. Cos of pi over 2 is just 0. And then cos of pi over 6 is square root of 3 over 2. In the denominator, we've got negative 4 sine 3 theta again. So we'll start out with negative 4, 1. The cos of, the 3. Did I forget my 3 there? I forgot to write my 3 right here for the chain rule. Sorry about that. So times the 3, and then the cos was square root of 3 over 2 at pi over 6 we saw, plus 4 cos 3 theta, we saw from above is just 0. And then negative sine of pi over 6 will be negative a half. Those ones go away. Negative 4's divide out, 1's divide out, 3's divide out. So this is really just 1/2 over square root of 3 over 2, which that's 1/2 times 2 over square root of 3. So this is just equal to 1 over square root of 3, or in other words, square root of 3 over 3. That's our slope. And because we had 0, 0 as our point, it's really like we have y minus 0, which is y. And then our slope times x minus 0, which is just x. So that is our equation of our tangent line for that first one. So case 2, we're going to look at the pi over 2 case. So we've got minus 4 times, when we put in pi over 2, we'll be doing sine of 3 pi over 2. So that's going to be negative 1 times 3 times sine of pi over 2, which is 1, plus we'll have 4 times cos of 3 pi over 2. Well, cos of 3 pi over 2 is just 0 times cos of pi over 2, which is 0. In the denominator, we're going to have negative 4. We'll have the sine of 3 pi over 2 again, which is just negative 1, times the 3, and this time we have cos of pi over 2, which is 0, plus 4 times cos of 3 pi over 2, which is 0, times the negative sine of pi over 2, which would be negative 1. Well, 3 of those spots are just going to wipe out as zeros. This is 0, 0, 0 for all of those. So this is just going to be 12 over 0. So we are undefined for our slope, meaning it must be a vertical line, and we are passing through x equals 0. So x equals 0 is just our equation for that vertical line. And our third case we had was 5 pi over 6. So we have minus 4. And then we'll have sine of 15 pi over 6. Well, if you divide those both by 3, you'll get 5 pi over 2. And that should be the same stuff as when you are at pi over 2. So we're going to have negative 4 times 1 times 3 times sine of 5 pi over 6. Well, 5 pi over 6 is a 30-degree reference angle in the second quadrant. So you have 1, negative radical 3, and 2. So we're going to have 1/2 for sine of 5 pi over 6. Plus 4. Cos of that 15 pi over 6, which is like pi over 2. So cos is 0 at pi over 2. Times cos of the 5 pi over 6. Well, the adjacent over the hypotenuse will give us negative radical 3 over 2. Over negative 4. We still have that same sine value. We still have the 3. But now we have cos of 5 pi over 6, which is negative radical 3 over 2. Plus 4 times cos of what can be thought of as the same as being pi over 2. So that's just a 0. And then times negative sine of 5 pi over 6. So we would get negative 1/2. The last two parts are just 0. In the front parts, the negative 4's divide out, the 1's divide out, the 3's divide out. So this is just 1/2 over negative radical 3 over 2, which is the same as we had in scenario 1, but with a negative. So this will end up being negative radical 3 over 3. So we just get y equals negative radical 3 over 3x, because remember our point was at 0, 0. So that's a long process to do 3 of them. If you had to just do 1, it wouldn't be quite as bad. One last one we're going to look at for today. So we want to find the slope of this curve at negative 4 comma pi over 3. Well, notice it's the same one that we used a second ago. So we had negative 4 sine 3 theta times 3 sine theta plus 4 cos 3 theta times cos theta over negative 4 sine 3 theta times 3 cos theta plus 4 cos 3 theta times negative sine theta. So if we're at pi over 3, that's 60-degree reference angle. So we're going to have that this is negative 4. 3 times pi over 3 is just pi, and sine of pi is 0. So we'll have times 3, sine of pi over 3, it doesn't really matter, but it's square root of 3 over 2, plus 4, cos of 3 times pi over 3, so that's cos of pi, which is negative 1, times cos of pi over 3, which adjacent over hypotenuse would be a 1/2. In the denominator, we'll have that same negative 4 times 0 times 3, but now we've got cos of the pi over 3, so that was our 1/2, plus 4 times the same negative 1 as we had before, and then times negative square root of 3, over 2, negative square root of 3 over 2 because there's negative sign of that. So the first two parts wipe out, the 4's divide out, the negative 1's divide out, and this is essentially the same thing we saw before, so it'll end up as negative radical 3 over 3. And all they wanted was the slope in this one. All right, that's it for today's video. Kind of a long process when doing the derivative of a polar curve. Have a great rest of your day.